ごきげんよう皆様、メインディッシュは完成します。As Tonio Tusardi from JoJo Part 4 on Diamonds Unbreakable would say, because finally we're at the end of the Cardano extravaganza, and we're going to find the general cubic formula simply using the depressed cubic equation and a clever change in variable. So recall that we have our general cubic equation, which is y of x equals ax cubed plus bx squared plus cx plus d, where a, b, c, and d are all real numbers. What we are going to do now, in order to find our change in variable substitution, is take the derivative of this function and set it equal to 0. So recall the power rule of differentiation, where n is your integer. If you do it correctly, you'll end up with y prime of x equals 3ax squared plus 2bx plus c. And this is essentially a quadratic being set equal to 0. So in order to get what the general form of x would be, we simply use the quadratic formula again. And if you follow the computations correctly, you end up with x equals negative b plus or minus square root of b squared minus 3ac divided by 3a, which is very similar to the quadratic formula equation over here. Now, do note that in the quadratic formula, the term negative b over 2a corresponds to the axis of symmetry. What is the axis of symmetry? The axis of symmetry is where the sign of your curve changes in terms of its values. Why? Because you're at a critical point. And so either your curve will pass the axis and therefore you will have a 0, or it will just turn around and only touch the axis that you're dealing with. So that's the case when your so-called discriminant term, b squared minus 4ac equals 0. That's what it represents. And so you have x equals negative b over 2a. But then what does this x equals negative b over 3a in the first derivative analog correspond to? Well, if this is where you have zeros and the signs of your function change, then this is the place where the sign of your derivative changes. And what's the point in differential calculus where the sign of your derivative changes? The inflection point, which is what you get when you take the second derivative of a function and set it equal to 0. So that's what it is. And the substitution we're going to make, which is often called a Viet substitution, is x equals y minus b over 3a. So let us go back to the depressed cubic now. I remind you that it is of this form. And all we have to do is simply plug in this new substitution into our function. Then set the whole thing equal to 0, and then compute what y will be. It's very useful in order to compute this that you use the binomial theorem. Here is its general form in combinations, which is malleable for positive integers, but also negative integers as well. And then, this is just a definition of a combination. And if your n is reasonably small, you can just construct the binomial coefficients for your expansion using Pascal's triangle. Then as you're building your terms, just get your left-hand term, raise it to the highest power, and then keep descending the powers by 1. And then for the right-hand term, start with b raised to 0 power and keep ascending the terms all the way up until you reach the exponent. And then do so forth. So if you do the algebra correctly, you'll end up with this expansion for the cubic binomial and this expansion for the quadratic binomial. Then simply go and combine these terms together. For your convenience, I've highlighted them in different color text. And as you've noticed here by this yellow highlight, the quadratic terms cancel. So we do indeed get the depressed cubic from this. It's magic. And just follow some highlight stuff here, blah, 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 tedious algebra. Here you have to go and find a common denominator. That's just multiplying something over something. blah, 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 not interesting. Okay, here we are. We end up with this equation, but remember that the depressed cubic has to be of this form. So in order to get our correct n, we simply have to take this constant term and then alternate the signs of these three terms. So this becomes negative, and this becomes positive. So we finally end up with this. And so our corresponding parameters of n and n that satisfy Cardano's depressed cubic solution is negative v squared plus 3ac all over 3a squared, and in prime factorization form, 3 squared abc minus 2b cubed minus 3 cubed times a squared d over 3 cubed a cubed. Oh, that was a mouthful. Now remember the parameterization we did for the depressed cubic? This guy, for instance? Yeah, and we ended up having this nested radical, this difference of nested radicals as our solution. Well, all we have to do is plug in these nightmare terms into there and make the change in variable, because remember, we let x equals y minus b over 3a. We're solving for y here, not for x. So the true solution should be this junk plus b over 3a. And if you combine them all together, you will get our solution in terms of cubic, quadratic, and linear coefficients and constant terms. And brace yourselves, people, this is what it ends up looking like. Oh my, that is so, oh my goodness. I only think there's one person who can really capture the essence of how to describe my feelings about this formula right now. Mankanshoku Mako-san! Thank you. Domo arigatou gozaimasu, Mankanshoku-san. You've truly captured the essence of the horror I feel about this. Now, sateto, where were we? Okay. If you try to come up with the solution on your own and you're not able to get this correct form, don't worry. We make mistakes all the time. We're human. I'm human. I've spent an excruciating number of hours going over the results and realizing I actually forgot the b over 3a change in variable factor and was solving for y this entire time. So it's really normal. And even then, if you cannot come up with the correct computation, you can still understand the bigger picture of what is happening during the transformations that help us find a solution. And I like to say we can do this by looking at the mappings of the transformations. So what is a brief mapping notation, in case for those who aren't familiar? We encounter them in pure math a lot. So it'll be for the real numbers for our purposes. And it's basically, you have a set, which is a collection of objects, set that is the domain, all possible inputs that you can put in your function, and then a codomain set, which is the set of all possible outputs that your function or machine can spit out. So we map from the domain to the codomain. And here's an example of one function. I'm arbitrarily mapping from 2 dimensions to 3 dimensions here. So going from a rectangular sheet of paper, like so, and going up to a rectangular prism. Or I could go down a dimension. I could go from the rectangular prism and then go to the rectangle. And expressing these in terms of set theory notation, if I say that R1 is an element of free space and R2 is an element of 2 space, then I get that the function will be defined as g of R sub 1 equals R sub 2. So here are a few big picture general mapping behaviors to notice what's happening in the solution space of the cubic. Let me know in the comments if there are any mistakes, just in case. So here's how I denote my spaces. You might either cringe at it or be, whatever. So the subscript indicates what number of mapping we're dealing with, starting with number 1. And the superscript indicates the dimension. So our subscript 1, superscript 2 indicates a 2-dimensional real space. The first 2-dimensional real space mapping, which is essentially the cubic function we are dealing with. We are now going to make the change in variable, and I think this mapping is either some kind of recursive thing you're doing, or it could be a permutation. Since you're mapping from the set y, this new change in variable you're doing, to itself, assuming of course we let y be an element of set y and x be an element of set x. And this corresponds to the definition of permutation from group theory. You just map a set to itself, and that basically rearranges the order of your elements, just like how you talk about permutations in combinatorics. Now let's look at our second mapping. Actually, sorry, our third mapping. We basically take our solution curve and we map it to the horizontal line. So we degenerate the curve. And finding the solutions of this would be the kernel of your map. So what you can think of this is I have a periodic trig curve over here, and I have a horizontal green line, x-axis. What you'd be doing is you'd be taking this sine curve, and then you'd be flattening it out to match up with the horizontal line. So that's what's happening in mapping number 3. Now, mapping number 4, we add in our multivariable functions, t sub m, comma n, and u of m, comma n, equals the ugly garbage. And then, sorry, in this fourth mapping, the composition depends on 2 inputs. So there's a total of 4 ways the multivariable function x can change at this layer. I just get this by multiplying the number of functions by the number of inputs I have. So 2 times 2, which is 4. Similarly, I go to the fifth mapping, and here's where we add in, we basically make a function of our terms m and n here in terms of the coefficients and constant terms of the general cubic. So we have 4 inputs now. And so since there's 2 functions, there's a total of 8 ways the multivariable function can change at this final layer. So in general, there's a total of 5 mappings. That's the way that an algebraist or a group theorist would take a look at what's going on with this problem. So a thing you might be wondering out of curiosity is how, in order to solve the general cubic equation, this guy, which is a single variable function, we had to end up turning it into this multivariable function. And I'm no expert in multivariable calculus or functional analysis or partial differential equations, but from what I've read up, a reason I think why we end up bumping up a dimension and actually getting up with a closed solution has to do with the Jacobian. Because the Jacobian basically is a factor you multiply to the differential every time you solve a multivariable integral. And that always distorts the area of your transformation. And if I recall, it does have some dimension shifting properties. Again, I could be mistaken with that. But I have an intuition that that is why we make we go from a single variable to 2 variable function or n variable function. Okay, so just a final endnote. Although I did mention that there was symmetry with the depressed cubic and possibly with this horrendous general cubic as well, that makes me want to cry. I don't think the change of variable x equals y plus b over 3a will help us find a solution because all the operations are addition. There will be no cancellation here, but maybe there's some clever computational setup you can put up and then you'll actually get the answer. I leave it to you as the viewer to try that out. And finally, one last meme before we go. I'm more sad looking at the general solution than at the depressed solution. I know, I'm sorry, that's probably corny as hell, but I couldn't resist. So that's it. I will upload my 3D volume arts and crafts Cardano video as soon as possible, but until then, I wish you a pleasant day. See you.